Bismillahirrahmanirrahim. Assalamualaikum and a very good day to all students. Again, I am Dr. Jeffrey bin Abdul Razak from the Faculty of Manufacturing Engineering FKP. So let us continue the offline lecture for this chapter 11, the characteristic, processing and application of composite. So this is the part 2 of the lecture. So for the first slide, like particle reinforced composite, okay, we also need to understand all related factors which might influence the resulted properties of fiber reinforced composite, the FRC. So let us first discuss our first factor related to the influence of the fiber length, all right? The fiber length here and the diameter of the fibers. So as you can recap from the previous part 1, okay, we already learned about the L over D, the aspect ratio. The higher the aspect ratio of the fibers used in the composite, the higher the performance of the composite will be. So as you all remember at the previous slide also, I've already mentioned that the fiber reinforced composite or FRC requires certain critical fiber length. So the critical length, the LC, so that the fiber can perform their function efficiently for efficient stiffening and strengthening effects. So by looking at to this equation here for the critical fiber length, the fiber length or FL, all right, or the LC here denoted as LC is basically dependent to the fiber diameter D, all right, multiply with the ultimate tensile strength sigma F times with 15 here, divide with the shear strength tau of the fiber matrix interface strength, the tau C here. So meaning to say, right, as you can see here, the critical length is basically on the order of millimeter, 1 millimeter. So for example here, for the case of fiberglass, all right, the fiber length of more than 15 millimeter is required or is needed for better load transfer efficiency. All right. So meaning to say when the sigma F value is 1, D value is 1, all right, and tau C value is 1. So we will have the fiber length we require must be more than 15 millimeter for better fiber efficiency. So the following diagram at both below left and right here showing you why the longer fiber is required to carry stress more efficient. For shorter fiber here, all right, we call them as a shorter fiber or discontinuous fiber. As we can see here, when the fiber in the matrix seems deformed around the fibers during the loading, all right, such that there is no virtual or no stress transfer happen and only little reinforcement effect is being introduced by the fiber. While this is not the case for the longer fiber here, where you can see here, the load given is homogeneously distributed or evenly shared by the matrix and the fiber. We can see here, the fiber reinforcement become very effective and the fiber is in this case, the continuous fibers are able to give significant improvement in the composite strength at the end. Better fiber efficiency can be seen here at the stress axial position. Stress axial position, right, longitudinal to the fiber orientation, and the applied stress is becoming equal to the fiber length. All right. So the next factor which influence the properties of fiber reinforced composite, the FRC here, is the fiber content or concentration. In fiber reinforced composite, the density rho here, the strength, the sigma, and the modulus E here, and the other properties of produced composite are basically depending on the fiber content. All right, to represent the fiber content, so we can represent it either by the fiber content, the fiber content, we can represent it either by the weight fraction W or the volume fraction V, denoted as W for weight fraction and V for the volume fraction. So the fiber volume fraction is basically defined as the ratio of fiber volume, all right, to composite volume, the overall composite volume. So we can have the capital VF here denoted as the fiber volume fraction, while the matrix volume fraction is defined as the ratio of the matrix divided by the volume of composite equals with the volume fraction of matrix. And same goes, these two definition implies to weight fraction, where the matrix weight fraction is Wm divided by Wc equals with metric weight fraction, the capital Wm, and Wf, the weight of fiber, divide with the weight of composite equals with the weight fraction of fibers. All right. So to simplify the understanding, so when we relate the volume fraction and also the composite volume, the volume fraction of the matrix and volume fraction of the fibers and volume fraction of the composite. So the volume fraction of composite, sorry, okay. So volume fraction of fibers, all right, is basically add with volume fraction of matrix equals with the total composite volume VC. And same goes to the weight fraction of fibers, WF here, plus with the total weight fraction of matrix, WM here, will always equals with total weight of composite, WC here. So the first equation here and second equation here, when we divided with the total volume of composite, okay, and also here when we divided with total weight percent of weight of composite, okay, so we will have something like this. I will write it down again. VF plus VM equals with VC, okay. When we divide with VC, okay, VC divide VM with VC, and then VC with VC, we will have the bigger capital of VF for volume fraction of fibers plus volume fraction of matrix equals with 1 unity. All right. Okay, and same goes to the weight fraction here. The WF plus WM equals with WC. Divide with WC here. All right, WC over WC here. Divide with WC. We will have the volume, the weight fraction of fibers plus the weight fraction of matrix equals with unity value of composite. All right. So when we relate it with the density, we understand that relation between the volume and mass could be established. Have a look at to this simple equation of density. Rho equals with mass over volume here. All right. Can be written as in equation 5 here. So from the weight fraction equation as discussed at the previous slide, which is WF plus WM equals with WC or unity 1 here, we can now substitute it into the weight fraction is equal to the density rho multiplied with the volume fraction, which is from here rho equals with W over V, W equals with rho V when we bring the V to the other side of equation. So the equation become the rho fiber. The equation here become as rho fiber times with volume fraction of fiber plus with the rho matrix times with the volume fraction of matrix equals with the density rho C, all right, of composite system composite volume of the type of the composite system times with the composite volume, right? Which is 1 after we divided it by its own VC. Okay, this is 1. All right, so then we will have this equation. So we have the basis equation basically as we can call it as a rule of mixture equation. Combination of the fiber part with the metric parts will produce the density of overall composite. All right. Okay, therefore, to derive the fiber weight fraction at the following equation at the bottom left and right here, the fiber weight fraction and fiber volume fraction, we can start somewhere from here. All right. So let's have a look to the clean sheet of paper here. All right. Okay. For fiber volume fraction, okay, as this equation at the bottom right here, all right. Okay, first we write down the fiber volume fraction, all right. Fiber volume fraction equals with fiber volume divide by composite volume. All right. At the composite volume here, all right, at the bottom here is equals to the fiber volume plus with matrix volume. All right. Next, by changing all the volume term in the equation with the relationship with weight and density, rho equals with W over V. So V equals with W over rho here. All right. We will find the equation at the end of derivation, something like this. So the VF, the fiber volume fraction, equals with WF over rho F divide with WF over rho F plus with Wm over rho m. Okay, great. So, okay, now to derive the fiber weight fraction, okay, the WF, the another question at the bottom right here, maybe we can start somewhere from here, make it the W as title of density equation. So we will have the, sorry, we start here, rho, wait, yeah. Rho equals with W over V. So make it W as our title of equation, rho V here. All right. So to find the fiber weight fraction, WF here, it seems like equal from this equation, rho F VF. Okay. So we will have the W equal with rho density times with volume. So for the fiber weight fraction, we can write it as WF equals with rho F times VF, like this. Next, divide the rho F with rho C for fiber density fraction here. Rho F over rho C times VF. The rho C at the denominator is actually equals with rho F over rho M plus rho, rho M Vm plus rho F Vf, okay, times with Vf here. All right. So now, after you get this equation, now you see the expansion of equation and do a bit of modification to equation by dividing all the terms in the fraction with the matrix density. All right. So from here, okay, after you get WF equals with rho F over rho MVF plus rho F. Sorry. Rho M V M plus rho F V F This is wrong, eh? Rho MVM plus rho FVF. Okay. Times VF, all right? Okay. Divide both up and bottom with rho M. Okay. So rho F over rho M V VM rho M VM over rho M plus rho F VF over rho M times with VF. Okay. Now you will have the equation similar like in this slide. Okay. Rho F, rho M over rho F, rho M VF plus VM times VF. Okay. All right. Okay. Same question. Both. After you simplify the derived equation, at the end, you will get the equation similar like here. All right. So next, factors which affect the final properties of fiber reinforced composite is the fiber orientation. Okay. So fiber orientation is related to the direction in which the stress or load is being applied. Okay. So meaning to say, if you have your fibers in this orientation, have a look at on the characteristic of loading direction or stress direction. This direction we call as longitudinal direction, but this direction we call as longitudinal transverse direction. Okay. The properties of FRC having its fiber aligned are highly anisotropic, meaning to say the fiber reinforced composite is having the characteristic of anisotropic where the properties are highly dependent on the direction in which they are measured. Let us first consider the behavior of a continuous and oriented fibrous composite that is loaded in the direction of fiber alignment, which is at the longitudinal direction. Okay, this direction parallel with the direction of fiber orientation. To start the derivation, first let's assume that the fiber matrix interfacial bonding is very good, such that the deformation of both matrix and fibers is the same, giving you the isostrain condition, which is the isostrain condition, meaning to say when the fiber deform, the matrix also deform. When the composite deform, both of the constituent also deform, giving you the isostrain condition. All right, where epsilon composite is equal, the epsilon composite is equals with epsilon matrix plus equals with epsilon fibers. All right, to start, the total load sustained by composite FC is equal to the sum of the load carried by the matrix. Okay. Okay. So to discuss here, all right. The FC here equals with FM plus FF. We understand that the sigma equals with F over A, right? So F equals with sigma A. From this simple definition of stress, sigma equals to F over A, all right? Thus, the force here equal to sigma A here. Whereas the cross-sectional area, the AC, AM, AF are possible. So you can write down here sigma CAC equals with sigma AM plus sigma F AF. Okay. Now substitute it, then divide all the area with the cross-sectional area of the composite. Now you divide all this with the AC, all right? With both left and right of the equation. So you will have sigma C AC over AC equals sigma M AM over AC plus sigma F AF over AC. All right, where AM over AC and AF over AC are the area fraction of the matrix and fibers respectively. All right, consider that in this composite, the matrix and the fiber phase length are all equal. So AM over AC is equal to volume fraction of the matrix, all right, VM. And then AF over AC is the fibers volume fraction, all right. So VF, all right. So as you can see here, we can substitute this VM and VF to the equation, and then our equation becoming sigma C equals with sigma M VM plus sigma F VF. Go back to the previous assumption of isostrain that epsilon strain composite equal to the epsilon strain of a matrix and equal to the fiber strain. Okay, so now divide all term, okay, all term here with the equation by its respective strain. So sigma C divide with epsilon strain, and then sigma M here, VM divide with epsilon strain, and then epsilon sigma F VF here divide with epsilon F. We understand that the stiffness equals with sigma over epsilon, right? So we can change at the end our equation into the modulus of elasticity equation, meaning at the end of derivation, we will have the modulus of elasticity of composite equals with the modulus of elasticity matrix times its volume fraction of matrix plus the modulus of elasticity of fibers times with the modulus volume fraction of fibers. So if you still remember, this derived equation for isostrain condition is basically similar to the upper bound equation. The upper bound equation for particles reinforced composite. All right. So next, we moved on to another possible extreme direction. So just now we talked about the direction longitudinal, whereby the deformation happen is in the form of isostrain. Okay, the transverse direction. Now we move forward to the transverse. Okay, this direction, right? When the load is applied is perpendicular at 19-degree angle. Okay, sorry, 19-degree angle. Okay, to the direction of fiber alignment, as you can see here, right? The isostress here, condition of 19-degree angle. In this transverse case, the stress sigma to which the composite as well as both faces are exposed is the same, or sigma C here, the sigma C here equals with sigma M equals to sigma F. This term we call as isostress condition. So for this condition, the strain or deformation of the entire composite, the epsilon C here equals with the epsilon matrix times the matrix volume fraction, epsilon M times matrix volume fraction, plus with the epsilon fibers times with the fiber volume fraction. But because of epsilon is equal to sigma divided by the modulus, okay, epsilon here equals to sigma divided by the modulus from these equations, from this equation, modulus equals with sigma over epsilon, all right? Okay. With sigma m over em time, but because of epsilon is equal to sigma divided by the modulus, we can rewrite it as sigma c over e composite, okay, something like this. The sigma c divided by modulus of composite, based from this equation, yeah, okay, equals with the sigma m, all right, the strength of matrix divided by the modulus of matrix, okay, plus with the sigma fibers over the modulus of fibers, all right, okay. What I'm talking about? Sorry. Uh-huh. Okay. I forgot about to multiply the equation here with the volume. All right. So we understand that the epsilon here is come from the modulus of elasticity equation. So we can change or substitute each part of this equation with their respective sigma over E. So as you can see here, the composite part here for their strain is becoming sigma C over EC equals with sigma M over EM times VM plus sigma F over EF times VF. All right. So by having this equation, now we divide it out and reduce the equation into this. All right. So the equation that we derive for the isostress condition is basically analog to this equation. All right. Since we understand that the sigma C equals with sigma M equals with sigma F, we divide all these terms with their own respective sigma. So what you can have after you divide it, you will have 1 over EC equals with VM over EM plus VF over EF. All right. Okay. So this following slide just to showcase to everyone that in overall, the modulus of the entire composite matrix and reinforcement phase is basically governed by the rule of mixture, all right? And it depends to the loading direction, where at the longitudinal direction, the isostrain condition is applied, where the composite will be having very stiff and also very strong. While at the transverse direction, okay, the isostress condition is applied, where the composite at the end behaving very soft and weak. All right, this kind of characteristic basically explain the anisotropic condition in fiber reinforced composite in FRC, where the properties are directional dependent. So next factors affecting the fiber reinforced composite properties is on fiber length versus its orientation. The rule of mixture also can be applied to the condition when the fiber orientation is random, short and discontinuous, not necessary for the fiber reinforced composite. We just refer direct to the continuous fiber or long fiber condition. We can basically estimate the modulus of elasticity of composite and the tensile strength of the composite, this continuous fiber reinforced composite, by considering the efficiency factor of the added fiber. So K is our efficiency factor. But this situation is valid only when the fiber length is larger than the critical length. Only then it will be applicable. Hope you still remember this law. So to determine the elastic modulus in fiber direction, the equation is E composite equals to EM, the modulus of elasticity of metric, times VM plus with K, the fiber efficiency here, times with EF, the modulus of elasticity of the fibers, times with the volume fraction of the fibers. All right. Okay. So as you can see here, of course, for the aligned case, K equals with 1. Okay, K equals with 1 for the align for the case of longitudinal fibers. All right. And then while K becoming totally zero when the fibers is in transverse or in isostress condition, as we understand just now. So at here, normally K value is basically less than unity, usually in the range of 0.1 to 0.6, 3.3/8 for two-dimensional isotropy, and 1/5 for 3D, three-dimensional isotropy. So to calculate the tensile strength here, just replace the E term here with the tensile strength term or tensile strength value for each respective matrix phase and also the fiber phase. For the case of align one-dimensional, the equation is similar with the isostrain condition here. So next, in fiber reinforced composite, the optimum strength and stiffness can be achieved in a composite by aligning the fiber parallel to the direction of loading, which is isostrain condition here, which is the isostrain case. However, the composite will basically poorly perform when the load is applied perpendicular. Okay, when the load, okay, say for example, this is your composite when the load is applied perpendicular, all right, which is the isostress condition. So to get balanced properties or more isotropic composite, we need to randomly orient the fibers into this condition within the matrix. However, there is a little bit drawback in decreasing a bit of the overall strengthening effect when we have this isotropic condition. Isotropic due to random fiber orientation. All right, next. We finish basically discussing the fiber reinforced type composite. Now we move forward to the next type of composite based on its reinforcement configuration, which is the structural composite. A structural composite is normally composed of both homogeneous and composite material. All right. So most important in structural composite, the properties are basically dependent not only to the properties of the constituent material, but on how the structural element geometry look like, the geometrical design of the various structural element. So laminar composite and sandwich composite panel, okay, we have two types of the structural composite, the laminate type, and sandwich type. Are two most common structural composite example. Normally, in structural composite, the sheet is basically being stacked, all right, and bonded with the stacking sequence of 0 degree alternatingly with 90 degree or any degree in between. Sorry, this actually referring to this explanation, all right? Okay. The stacking method of give balance properties. Okay, this stacking method will give balance properties with in-plane stiffness. For sandwich panel, it combines the low density of honeycomb here, all right, as a core with face sheet. The face sheet bonded together with the adhesive layer. In sandwich panel structure, it gives benefit, of course, due to the hollow nature of the honeycomb structure, the small weight and large bending stiffness. In this following slide, I will detail out the type of structural composite. We start first with the laminate composite structure. Okay, this is the lamina composite structure. This is a traditional type of structural composite. Two or more layers of panel are being stacked and bonded. First layer, second layer, third layer, fourth layer, being stacked together and bonded together as an integral piece. For example, the wood, the thin wood, in which layer by layer of the same wood, but the grain orientation are different in their orientation to increase overall strength of the laminate composite, the laminate piece. In lamina, a composite has relatively high strength in a number of directions in the two-dimensional plane. However, the strength in any given direction is of course lower than it would be if all the fibers were oriented in that direction. The second type of the composite, okay, is the sandwich structure with the foam core at the middle. As you can see here, a sandwich panel consists of two outer shell at the top and at the bottom here, that are separated by and adhesively bonded to a thicker core here of low density foam. All right. Sandwich structure using the foam core. Okay, next. For the third category of structural composite, it is the sandwich structure with honeycomb structure at the middle here. All right. So as an alternative to foam core, due to the lightweight characteristic of the honeycomb structure, all right, either foam or honeycomb basically achieve high strength to weight ratio and stiffness to weight ratio properties. Some of the application example, all right, by using the structural composite of sandwich or laminar structure is automotive tire, all right, where inside the tire, basically, it consists of multiple layers of reinforced rubber that are bonded together. Some of the fiber reinforced composite, which having multi-layered fiber reinforced plastic panel for aircraft, all right, automobile, body panels, and body boat hulls. Next example is the printed circuit board here. Consists of layer of reinforced plastic and copper for better electrical conductivity and insulation behavior. The snow skis, all right, having the composite structure that consists of metal layers, all right, particle boards and phenolic plastic. And also the windshield glass for your automotive car, all right, it actually consists of two layers of glass on either side of a sheet of tough plastic. All right. So similar to fiber reinforced composite, in composite design, we always look for the balanced isotropic properties to ensure the strength of composite are all equal at any direction. Hence, for the structural composite, it is also the same. In producing a more isotropic composite is by using the multiple plies of continuous fibers. Okay, this consider one ply to another ply. All right. Okay, with the orientation of fibers are differing in each ply. So every single ply in the stack are oriented at different angle. All right, so you see here, the fiber can vary by 90 degree, 45 degree, and 30 degree. 30 degree here. Sorry, can be 30 degree also. So the degree also can be orient either in the negative or positive direction. Okay, next, as to recap the purpose of having composite in different class of composite classification based on the metric used. First, for the CMC, for the ceramic metric composite, the main aim is basically to increase the toughness. Ceramic body is normally brittle, So by reinforcing it with the particle or fiber reinforced phase, we can see here the strength of the fiber reinforced composite are increased, and presence of fiber at the same time may increase the ability of ceramic body to absorb the energy due to the increase of toughness. While in the polymer matrix composite making, we are very much interested to have the increase in specific properties. Okay, as you can see here, the PMC here, because of it is light, we are really much interested to have increase or improvement in these specific properties due to the lightweight and lower density characteristic of polymer as metric. You see here, by using PMC, it will increase the modulus E here, in and specific modulus in comparison to unreinforced polymer at here, but by using PMC, the specific modulus or the modulus here are significantly increased. All right. But for the metal matrix composite, you can see here the presence of disperse phase in metal composite increase the strength at higher temperature. So comparison between the 6061 aluminium with the 6061 aluminium reinforced with the silicon carbide viscous. You can compare here between the plain aluminum alloy with the composite of MMC having the SiC viscous. So here we can say that the purpose of having composite is at least improving the properties of original material. In this case, the ceramic, polymers, and metals. So we already covered completely covered the first classification strategy of composite based on the type of disperse phase, which are the particulate, the fibers, and the structural types of composite. Next important way to classify the composite material is based on their metric phase. So we have here three main classification for this kind of composite classification or categorization. The polymer matrix composite, PMC, the metal matrix composite, MMC, and then the ceramic matrix composite, CMC. This is PMC, MMC, and CMC here. But for each of these classification, again, we will have another sub-classification. For example, if you remember the polymer having two types of polymer category, the thermoplastic-based composite and the thermoset-based composite. Same goes to the MMC and CMC. I will explain further details for each composite classification based on the matrix type in the following slide. Yeah. So we will start with the polymer matrix composite PMC. So in this subject, basically we will give detailed emphasis to PMC as the application range by using PMC is very much wider for many engineering application using the PMC. So for the PMC itself, as the name implied, we can simply understand that the polymer resin becoming as continuous phase, which matrix, while the reinforcement medium are consist of fibers or particulate or etc., which can come as polymer itself or ceramic or metallic material as a dispersed phase. So PMC is used in the greatest diversity of composite application at largest quantity, since this kind of composite can be processed at lower temperature or even at room temperature. All right. Easy manufacturing process for fabrication and also very cost effective. All right. So the most important common of PMC are glass fiber reinforced polymer GFRP, carbon fiber reinforced polymer CFRP, and then the aramide fiber reinforced polymer AFRP. So all these PMC are reinforced with high performance fibers made up from glass, carbon, and polymer-based aramide. So for the PMC GFRP, all right, this is the GFRP in short. CFRP. The composite which containing of glass fiber, either continuous or discontinuous type as dispersed phase within a polymer matrix. All right, discontinuous glass fibers or continuous glass fibers within the polymer matrix. In real world, this type of composite are manufactured at the largest quantity. All right, these are two types of glass fibers, either as E-glass or S-glass. And for the dimension, the glass fiber are normally having the diameter range at between 2 to 20, 3 to 20 micron meter. So please recap back the lecture content from the chapter 9 on how we manufacture or how we process the glass fiber manufacturing. Okay, so just to highlight why the glass fiber are very popular as fiber reinforcement, it is actually due to several reasons. Due to it can be easily drawn into the high strength fiber from the molten state. All right, and in addition, it also readily available and economically reasonable for wide variety of composite manufacturing technique. As the glass fiber is relatively very strong, and when embedded in a plastic matrix or polymer matrix composite, we can gain a very much or very high specific strength of produced composite. Other than that, what makes the glass fiber popular are their inertness, very inert, lengai, which render the composite using glass fiber as reinforcement useful in corrosive or reactive environment. Okay, so just to highlight on some important points related to glass fibers for composite application. Again, this is most widely used fiber as it possesses several benefits. All right, like low cost, corrosion resistant, and low cost relative to other composite. Normally, the glass fibers is used for composite piping production, fiberglass tank, boats, and sporting goods. All right, this is for the application. And then, however, the glass fiber also possess some disadvantages which limit their usage, such as it possess relatively low strength in comparison to carbon fibers or aramide fibers, high elongation and moderate strength and weight. There are two possible kind of glass fibers, which are the E-glass fibers and S-glass fibers. E refer to the electrical type, which cheaper in its price, and S refer to the high strength type of glass fiber. This is how the glass fiber look like. Okay, all right. So we can have the matte glass fiber in the form of woven glass fiber here, the chopped glass fiber as dispersed glass fiber phase configuration. Now we move forward to the next example of the polymer matrix composite using the carbon as the dispersed phase. We have the CFRP here. The carbon fibers reinforced polymers. Okay, if the GFRP is popular due to its lower cost, but the CFRP is most preferable for high performance application. Okay, carbon fiber possess the highest specific modulus and specific strength as compared than other reinforcing fiber material. Okay, so it able to retain high tensile modulus, high strength at higher temperature with oxidation resistant. This kind of fiber also are very hydrophobic. All right. So hydrophobic meaning not attracted to the water and moisture, which are not affected to moisture or wide variety of solvent, acid, or alkali. The carbon fiber exhibits superior physical and mechanical characteristics, which allowing them to be incorporated in composite for better specific engineered properties. So using the carbon fibers also allowing the inexpensive and cost-effective composite manufacturing process. All right, so this is how the carbon fiber look like. All right, in the matte form, the carbon fibers is the second widely used fiber after the glass fibers. So it was highly used in the aerospace application and also for the sporting goods. All right, it possessed some advantage like high stiffness and also high strength with low density. So it is good for the specific properties of, say for example, E over rho and then sigma over rho. This is the specific properties. Specific properties. Because of it is really lightweight in terms of their weight, okay? So it will give a lower value of rho. So at the end, it will increase the specific properties of stiffness, modulus, and also the specific properties of strength. So carbon fibers possess high modulus up to 900 gigapascal. So it is too high, it's really high, with diameter maximum at 8 micron, all right, which is smaller than human hair, where the fibers is basically grouped into tau or yarn, having about 2 to 12 thousand fibers. So the last example of popular fiber type used in PMC application is aramide fibers. So aramide fibers, also known as Kevlar fibers in reinforced polymer composite. Aramide fibers normally used for ballistic products such as the bulletproof vest and body armor for the defense industry, the protective clothing and sporting goods. You can see here the aramide fiber image in the yarn, all right, okay, and matte type aramide fibers, and also in the chop condition. On its characteristic, aramide fibers is high performance replacement for glass fibers, all right, and it possesses higher strength and lighter weight in comparison to glass fibers. But most interesting, it is more ductile than carbon. So by having the aramide fibers, it can give possible improvement in terms of toughness behavior for the composite. So for these next two slides, you will briefly expose with another two types of composite classification based on its matrix. We will have the ceramic matrix composite, CMC, and the MMC, metal matrix composite. For MMC, it basically used especially for CMC, I'm so sorry, especially used for application that require high temperature resistance, where resistance to high temperature is required, and high corrosive environment is desired. All right, CMC are very strong and but it is very lack in terms of ease, toughness, or ductility because the nature of the ceramic material, okay, is really brittle. But having the CMC, it is much better in comparison than ceramic itself. So the metric used for CMC are like the silicon carbide, the SiC here, the silicon nitride, SiN here, and aluminium oxide or Al2O3, Al2O3, and mullite. Mullite is the compound of aluminium, silicon, and oxygen. All these CMC metric could retain the strength up to 3000 degree Fahrenheit, very high temperature. So the fiber material we normally add to ceramic matrix composite for CMC fabrication commonly are carbon and aluminium oxide, alumina fibers. Yeah, this is in short we can say as alumina fibers. Some of the application of CMC are they used in jet and automobile engine, and deep sea mining, cutting tool, and pressure vessel. So you see here all the application which require high temperature resistance and durability toward abrasive wear and tear condition. So CMC is the best candidates for us to use. Okay, the last slide for part 2 of composite lecture, we will talk about the MMC, the metal matrix composite. MMC is used for higher service temperature than their base metal counterpart. The presence of reinforcement within the metal matrix may improve several properties like the specific properties, the abrasion resistant, creep resistant, thermal conductivity, and dimensional stability. So basically, MMC offer advantage that they can be operated at higher temperature with non-flammable and greater resistance to degradation caused by organic fluids. However, MMC, as we know, is a bit pricey, expensive compared than PMC, the polymer matrix composite. So for MMC, the matrix used are like the super alloy, as well as alloy of aluminium, magnesium, titanium, and copper, while the reinforcement phase used may be in the form of particulate, both continuous and discontinuous fibers, and viscous, which normally added at the concentration at between 10 to 60 volume% of addition. Continuous fibers added to MMC are like the carbon fibers, the silicon carbide, the boron, aluminium oxide, and the refractory metal, the higher temperature metal. While the discontinuous reinforcement are like silicon carbide viscous, chalk fibers of alumina, carbon, and particulate of silicon carbide and aluminium oxide. So this is the end of part 2, and I believe you must stay tuned with me for the following part 3 offline lecture of this chapter. With that, I thank you and see you again at the part 3 video presentation. Thank you.